A year ago, the United States government released this report on secure and measurable software. And the press release said future software should be memory safe, and it called for the use of Rust over C and C++. I read this report on my flight to S4 last year, and I sat overlooking South Beach and wrote an essay summarizing my thoughts. And this essay is available on my personal blog and is the motivation for this talk, in combination with using Rust in order to write software for critical infrastructure over the past year. My takeaways from the report were, on the positive side, I was really pleased to see explicit advocacy for a memory-safe programming language, and especially Rust, given its great tooling and great performance. I was pleased to see a broad definition of software verification, not just a focus on formal methods, and it encouraged measuring and visualizing software quality in order to make progress on quality in a large organization. Now, where I thought the report missed the mark, it didn't address what to do with the vast amounts of C and C++ that exist in the world that aren't going away for years and probably decades. I was particularly surprised that it did not encourage software isolation in the form of virtual machines and other techniques, and it had a rather strange emphasis on astronautics without much mention of critical infrastructure, which of course is the focus of this conference, and where memory-unsafe code can have a much larger impact on our day-to-day lives, I would argue. So this talk is going to focus on Rust, an increasingly popular systems programming language that has the performance of C and C++, but memory-safe guarantees that eliminate entire classes of security vulnerabilities. And if you're new to Rust and you need an introduction, especially in the ICS context, I encourage you to watch this talk by Adam from S4 in 2020. I want to explore 4 questions in this talk. Rust is a memory-safe language, but is it really that safe? And I'm going to spend most of the time on this question. Rust is often touted as a replacement for C++, but is C++ really that unsafe? Third, how can we improve software isolation independent of the programming languages we use? And finally, how can we visualize software quality in order to make progress on quality and security in a large organization? So the first question, is Rust really safe? Consider this function in Rust that indexes into an array at a given offset. And then I'll call that function from a Rust program with an offset that is outside of the bounds of the array. Now, unlike C and C++, Rust will panic and terminate that program, ensuring the memory-unsafe code is never executed. This is one of the memory-safe guarantees of Rust. But if instead of indexing into that array using safe Rust, I use unsafe Rust and dereference that pointer myself, well, then the program will run and happily execute that unsafe code, returning a value. In other cases, it might crash. We're in the land of undefined behavior and, of course, security vulnerabilities. Now, programmers use unsafe Rust for performance, for managing memory, and for interfacing directly with hardware. You can't use unsafe Rust by accident. You have to opt in to using it using this unsafe keyword. So that's a nice property of Rust. And the unsafe keyword also allows us to pay extra attention to these parts of the code, either in code review or through tooling. So that's an advantage over C and C++. How prevalent is unsafe Rust? This paper estimates that about 30% of all Rust crates incorporate some use of unsafe Rust. And this paper, which is focused on embedded systems, which of course are very common in ICS and in IoT, unsafe Rust is about twice as common versus normal. So that brings me back to the question, is Rust really safe if we have all of this unsafe code, and what can we do in order to secure it? So in C and C++, there are sanitizers. These are dynamic analysis tools that can be used to identify memory errors or concurrency errors. And it turns out that the exact same sanitizers can be used in Rust. And the reason for this is that Rust, through its compilation chain, eventually ends up in the LLVM intermediate representation. And so we can take advantages of these sanitizers that were largely developed at Google over the past decade to secure things like the C++ in the Chrome web browser. So if I return to that unsafe code in Rust, I can run it with the address sanitizer enabled, and the program will immediately terminate with a memory error and generate this report. And if I zoom in on that report, you can see that it identifies a stack buffer overflow, and it identifies the specific function in which the memory error occurs. So the advantages of sanitizers, they're easy to use, and this is a well-known and proven toolchain that comes from LLVM. In terms of limitations, these are the same limitations that apply to sanitizers in C and C++. Some of them are incompatible, so they need to be run independently. They are dynamic analysis tools, so they only detect errors in code paths that actually get executed, and those two things combined tend to lead to an explosion of test cases. They're also resource and performance intensive, so they can't necessarily be run in production environments or in embedded environments. Now, this paper determined that about 70% of Rust developers are calling unsafe code through foreign functions. And foreign function interface, or FFI in Rust, is how Rust calls libraries written in C and in C++. And if I reflect on my experience with Rust in the past year, I've never needed to write unsafe Rust, and I think it should be exceedingly rare that an application developer like myself ever has to write unsafe Rust. But if I look at the libraries that I'm using, many of them are still in C and C++ with unsafe code. So I've been using SQLite, which is the most popular database in the world. It's installed on the order of trillions. Everyone in this room has SQLite on their phone. It's in every web browser. It's in many IoT systems and in many industrial control systems. It's written in C. DuckDB is written in C++, and the OPC UA library that I use from a Rust library is all C under the hood. So what can we do about this? Well, if you have access to the source code of those libraries, you can also enable the sanitizers there, and both Rust and the C or C++ code can be analyzed at the LLVM IR layer. So I can add calling foreign functions to the list of advantages of sanitizers. So let's take a look at what this looks like. Again, you have to have access to the source code to do this. Here's some code in C that has undefined behavior in the form of a buffer overrun. I build that C code in Rust using Clang and enabling the address sanitizer. This is how C code is ultimately called in Rust. It must be wrapped in one of those unsafe code blocks. And then that Rust function can be called from a Rust program with a string that's much too long and will overrun the buffer. And when it's run with the address sanitizer, again, the program immediately terminates with one of these error reports. And if I zoom in again, I get a stack buffer overrun, and I get a really nice call stack that goes all the way from the Rust code into that library in C. And the reason is I have the sanitizer enabled in Rust as well as in the C library. Now, a complementary tool to these sanitizers for detecting undefined behaviors in Rust is MIRI. MIRI operates at the mid-level intermediate representation, so it's kind of halfway between the static analyzer and these dynamic analysis tools like the sanitizers that I just described. And if I go back to this program that has unsafe Rust, and I run it with MIRI, MIRI will immediately identify the memory error, and it gives a very clear error message and even points to the line of code that causes the problem, not just the function that it's in. The advantages of MIRI: it's easy to use, provides clear errors with references to the lines of source code, and it runs all checks at once. So the sanitizers need to be used independently, but MIRI is going to check all undefined behaviors in a single pass. In terms of limitations, MIRI only detects errors in executed code paths, so it's similar to dynamic analysis tools in that regard. And it cannot interpret C or C++ called through those foreign functions, although there's experimental work going on in this area. Approximately 20% of all functions in the Rust standard library use some form of unsafe code. And I just want to call out this collaboration between AWS and the Rust Foundation in order to verify the standard library using some of the tools I just described, as well as some tools that I'll explore in the rest of the presentation. I think this is a really great effort for the community. So that brings me back to the question, is Rust really safe? Yes, but we need to be careful about unsafe code that's in libraries, as well as unsafe code that we're calling in C and C++. And just like in C and C++, we need to bring tooling to make sure that our code is safe. There's no free lunch. But of course, in critical infrastructure, which is one of the focuses of this conference, and this is the area that I work in, I work on utility scale batteries like this, We're not just interested in memory-safe code, we're also interested in correct code, because a software malfunction can damage property or endanger lives. So if I return to that Rust program, and in this case, this is the safe version, recall that if I run it, the Rust runtime is going to terminate that program, ensuring the memory-safe code is never executed. That's great. But this program might malfunction like this at an inopportune time, or it could be used in some form of denial of service attack. So how can we find errors like this, even in safe Rust? One tool that can help here is property testing. Property testing is used with unit tests that take some form of input. They can then be wrapped in the property test macro, and property test is going to generate random inputs to those tests. And it's best demonstrated by just running the tests. So it picks a random integer, the test fails. It picks a smaller random integer, the test fails again, and so on, all the way until it finds the boundary case, which of course in this case is the index 4. What property test is not good at is finding errors that are very improbable. So this function is only going to fail 1 out of 2 to the 64 if you're picking random input. So it's overwhelmingly unlikely that you're going to find an error here. And most of the time when you run prop tests, it's going to do its 256 iterations and declare everything's good. So property testing, it's easy to use. It's written in Rust and resides right alongside your source code, which is great. And if it can find an error, it can often refine that all the way down to the failing edge case so you know what to fix. In terms of limitations, the input is just random, and it only goes through a limited number of iterations, and it's not exhaustive. But of course, we could test this function exhaustively. I could just loop over the entire input space, and then I would know where it fails. But even if this assertion takes roughly a nanosecond, this test would take 500 years to run, which is just like boggles the mind. And if we had nested loops, this becomes impossible. So often, exhaustive testing is just not a tool that we can use. Connie is a tool that we can use in situations like this. Connie is a model checker that uses mathematics in order to verify that a program is correct within given constraints. And Connie operates on the mid-level intermediate representation, similar to Miri, but it generates a go-to program that's ultimately executed by the C-bounded model checker. A bit more on that in a minute. Connie uses proofs, which look somewhat similar to unit tests. They're also written in Rust and reside right alongside your source code. And then Connie immediately identifies this integer overflow error in the function before. You can also then run Connie to get a little code snippet that actually demonstrates the error so that you can identify it and fix it. Advantages of Connie, it's easy to use. It's similar to unit testing. You write it in Rust, resides alongside your source code. I think you can see a theme developing here of the tooling in Rust being very, very easy to adopt. It mathematically evaluates all inputs satisfying constraints, so it's exhaustive in that sense. In terms of limitations, if there's loops in the program, it needs to unwind them in order to keep the analysis feasible. That's why it's called a bounded model checker, so it's not exhaustive in those cases. And it does not currently support concurrency. Finally, it cannot check C and C++ code called through foreign functions. However, if you have access to the source code again, you can apply the C-bounded model checker directly. And this paper is a really great story about how Amazon did that internally to verify their C and C++ libraries, some of which are used by their customers. So I think I can finally answer the question, is Rust really safe? The answer is yes, but it's not as safe as you might think. You need to be careful of unsafe code called in libraries, as well as unsafe code that's brought in through C and C++ through foreign functions. So it's not as simple as just use a memory-safe language or just rewrite our code base in Rust. The good news is that in Rust, the wealth of tooling is really amazing. And I think adopting Rust, not just because it's a memory-safe language, but because it has fantastic tooling, some tools I've mentioned here, some I haven't, is one of really strong reasons to adopt Rust. Okay, the second question, is C++ really that unsafe? Here, I'd like everyone to listen to Bjarne Strustrup, who is the creator of C++. He's given a couple of talks on this subject, and he's written a couple of papers, one as recently as last week. The first thing to do is to separate C and C++. It is very difficult to write safe C. But the whole point of C++ has always been to write safer code. It's the reason for the standard library. It's the reason for patterns like resource acquisition is initialization, kind of a funny name, RAII, as well as other things in C++. What C++ has not done is deprecate features. As soon as you do that, then people won't update their compilers, and that introduces a whole nother set of problems. What Bjarne has encouraged is the adoption of the C++ core guidelines, which has profiles for type safety, bound safety, and lifetime safety. And if you're writing C++ 23 with these profiles enabled, the memory safe guarantees come very, very close to what Rust can deliver. So what's the problem? I encourage everyone to read this extremely pragmatic article by Herb Sutter, who's been on the C++ standards committee for many years. In it, he says that the problem is it's just too easy by default to write unsafe code in C++. The problem isn't that if we move all of our unsafe code in C++ to Rust, that we will have solved our problems. If we're writing a memory manager in Rust, we're probably using just as much unsafe code as we would in C++. And the problem isn't that C++ developers aren't trying hard to do better. The problem is that it's too hard to do the right thing. Just as an example, if I look at clang tidy, there's over 600 checks. Which one should I be using? And how do we have consistency across compilers? So in terms of safe C++, any improvements we can make here can impact the vast amounts of C++ that exist in the world, and we should continue to invest in that. In terms of limitations, C++ is unsafe by default. It doesn't have that opt-in to unsafe code like exists in Rust. And the community needs to keep investing in a safe subset that's easy for everyone to adopt. Now, software systems in ICS and IoT tend to be monolithic. And if you can compromise one part of the system, you tend to compromise the whole system. And I'm surprised there hasn't been more attention to software isolation in these contexts, independent of the programming language that's being used. So WebAssembly is one way to achieve isolation. WebAssembly is a compilation target that can be used from Rust or C++ or C, and it's ultimately executed in a stack-based virtual machine. So that's how it gets its isolation. It's portable in that it can run in the browser, or it can run on the server, or it can even run in an embedded system. And it has performance that's roughly native. WebAssembly continues this trend of isolating code from hardware further and further through various levels of abstraction and isolation. And if you want to deep dive on WebAssembly in an ICS context, see this talk I gave at S4 a couple of years ago. Another way to isolate code is using micro-VMs. Micro-VMs you can think of as somewhat similar to containers, but they don't share a kernel. They each have their own individual kernel, increasing the isolation. An example of a micro-VM is Firecracker, which was developed at AWS, and that's how AWS Lambda is run, where, of course, AWS is executing all sorts of untrusted code from their customers in a safe environment. So isolation allows us to run code safely in an isolated environment like WebAssembly or like micro-VMs, independent of the programming language we're using. Could be memory safe, might be not, could even be legacy code. And it also allows us to set strict resource limits in terms of memory, CPU, and I/O. In terms of limitations, this is an unproven technology in critical infrastructure and in ICS. It's also continues to evolve, so it becomes somewhat hard to adopt, and there is a learning curve and there is some churn involved. And one thing I'd like to call out is that some of the WebAssembly runtimes are written in C, and if anything should be written in the memory-safe language, it's the runtime for WebAssembly. The runtimes for the micro-VMs are generally written in Rust and do use minimal unsafe code. Finally, how can we visualize software quality? We have all of this software within our organization. We have all of these tools for making it better. But how can we make progress by making it visual? And that's one of the important things that the report pointed out, is that if we don't make it visual, we won't make progress. This was also one of the important conclusions of the Accelerate book that came out a few years ago. So Michael Feathers, who's well known for his book on legacy software, proposed this quality views idea, although he regrets the name. And he introduced it in this presentation a few years ago. And what he was saying was, if you had to make quality improvements or security improvements to the system on the right, it would be easy to explain to someone that that's going to be more complex, take longer, and introduce more risk than the system on the left. And you could even explain that to someone who's non-technical. So I wanted to take this idea from Michael Feathers, and I collaborated with him a little bit. I wanted to take a typical systems block diagram, introduce this notion of complexity that he had, as well as showing some change over time. And this was my take on quality views. So it's a typical systems block diagram, but enhanced with trust boundaries, the magnitude of data flows, the size and number of servers or components, and so on. But most importantly, using color in order to represent some kind of scoring of quality in the system. And then using that color, we can demonstrate changes in quality over time. Perhaps you've made an investment from Q2 to Q3 in order to improve quality. In terms of the context of this presentation, we could represent quality by scoring a component based on the tools that I've described. So if that component is running in isolation, and you've used fuzzing, and you've used memory, and so on, the more tools you've used, the higher the quality. So a typical systems block diagram on the top doesn't actually communicate that much information. The quality view on the bottom communicates a rich set of information. And this was actually the picture that said to me, quality views are useful. We were having a discussion over an image like this in a meeting, and someone said, hey, wait, we've made so many investments in security, how come that one component is still so red? And then we had a great discussion as an organization on the trade-offs we were making and the risks we were taking. So I hope I've convinced you that it's not as simple as just using a memory-safe programming language. And in summary, I'll just review the 4 questions that I posed. Is Rust really safe? Yes, but it's not as safe as you might think. There's no free lunch. Beware of libraries that use unsafe Rust, as well as the C and C++ that you might be calling through foreign functions. My call to action here is to use the wealth of tools in Rust for correctness and safety. Is C++ really unsafe? Yes, but modern C++ is not as unsafe as you might think. It comes very close to Rust in terms of memory-safe guarantees with consistent adoption of the C++ core guidelines. My call to action here is for the C++ community to continue to define a safe subset of C++ that's easy for everyone to adopt by default. How can we improve software isolation? I think micro-VMs and WebAssembly are 2 really interesting technologies. My call to action is that these probably need more attention in OT and in ICS. And finally, how can we visualize software quality in order to make progress on quality and security in our organizations? I propose quality views. Call to action is to give them a try, especially with your colleagues who are not programmers. If you want to read the motivation for this talk in written form, this is the essay that's on my personal blog. If you want my experience using quality views in a large organization, read this essay. And if you want to dive really, really deep in the Rust tooling that I described in this talk, as well as some tools that I didn't describe, and there's lots of references to other talks and to papers, see the latest 2 articles that are on my blog. And that's it. I'm happy to take any questions if there are any, and I think there's a microphone on either side.
Maybe a little out of scope what you were talking about, but I'm really curious for the visualization tools. First of all, a huge fan of being more safe by default. But the question about the visualization tools is there any research or data on the scoring systems that you pick that says those actually do make a significant difference in the outcome? I have this fear in the back of my head that a lot of what we do is just based on tradition, and would love to hear that maybe you have a source for picking good scoring tools.
Yeah, I don't think it actually matters so much what you score. It's that through the scoring, you end up having conversations as an organization that you wouldn't have otherwise. Like that's the really magical point of doing it. So don't fret too much whether you have a perfect scoring system. I think it would be, I don't know of a paper where someone has studied this. I think it would be interesting to see. I guess I would reference the Accelerate book, because in there, they're not looking at security in that context, they're looking at quality. But there is research that's based on someone's PhD research, basically, and stating that if you don't make things visual, you're just not going to make progress on certain things within an organization.
Yeah. All right, thank you.
Go over here. There's been some conversation in the research communities about code rewriting. Into Rust, I think DARPA has a program called Tractor, Translate All C to Rust.
That's right.
I know that's not the topic of your talk, but was just wondering if you had any thoughts on that, recognizing obviously the complexity and challenge of that problem.
Yeah, I think the DARPA program is very interesting. I've also given LLMs myself, unsafe code in C or C++, and it is interesting. Sometimes they'll eliminate the security vulnerabilities in the rewrite. I think this is very interesting. I guess if you can eliminate the need for C and C++ libraries that are being called from Rust, I think that's a huge improvement. There is actually an effort out there right now to rewrite SQLite in Rust. Where I would still be careful is, in some cases, you're going to need to use unsafe Rust to write a memory manager or to interface with hardware. So it doesn't make unsafe Rust go away entirely. And I think these, we're going to rewrite everything in Rust and then we're safe, is a little narrow in the thinking.
Thank you.
Brian.
Hey, Colin, great to see you again. Wonderful talk. Many of us are on the clock for creating a memory-safe roadmap, and I think your talk just gave a lot of fodder for that. Could you comment if quality views are, in your opinion, a good way to approach a memory-safe roadmap? And question number two, if you dare, could you weigh in on whether Rust TLS is a good idea for the OT community?
Can you repeat the last question?
The Rust TLS project as a replacement for Open SSL.
Yes, I think that's great, and I have been using it. And if I look at large parts of the Rust community, there's a lot of momentum behind the Rust TLS project. Your question on quality views, the reason I experimented with quality views and collaborated with Michael was within the very technical teams in our organization, we all saw the problems in terms of quality or security. But as soon as the conversation went outside the technical teams and you're trying to develop roadmaps and you're working with product managers and so on, it was very hard to prioritize. And it was actually quality views that unlocked the discussions. So I'm a huge fan of I think it would make a lot of sense to develop a security roadmap around a quality view, because it allows the whole organization to collaborate, not just the technical people.
Hi, great presentation. I see this kind of as a call for action for manufacturers, because they can maybe build future devices in Rust, but what about the operators that are sitting in OT, are sitting on 99% legacy devices sometimes, and those are in C, C++, and they're not going to be rewritten, and they're not going to be, even with the Tractor, they're not going to be migrated into Rust. So the question is the impact of this whole effort. How large do you think that is going to be, and how long is it going to take before the industry shift happens? Because we talk about Rust today, this year, last year, and then is it 30 years when something actually happens in, the last legacy devices go out of production?
Yeah, it's a huge issue. I think, as a customer, you need to ask these questions of your vendor and set expectations on your vendor of moving to memory-safe languages. Maybe some of those vendors are no longer in business, and this creates huge problems. This is one of the reasons I think there should be much more emphasis on software isolation, not just rewriting into Rust, because you can in that context, we could even take legacy code and run it in a safe environment that has much better protections. It's going to take a long time to get rid of unsafe code, for sure.
Right. Thank you.
Just a real quick question, follow up on the legacy code. Is there any initiatives to make an extensive set of tools for updating that legacy code, somewhere along the lines of MISRA-C, CERT-C, sort of like code scanning to correct for these unsafe practices in a more automated sort of fashion to make the updating the legacy code faster?
I mean, all of the tools I've mentioned through the talk can be used in your like CI/CD tool chain. Like something like Miri runs fairly quickly. You can run it as part of your build. There's a lot of investment going on, in tooling that can be used through automation to detect these errors. The biggest challenge would still be running the dynamic analysis tools. You need to set up an environment where you're actually exercising those code paths. I think that still takes significant investment. That's why tools like Connie, which is a model checker, and Miri, which is an undefined behavior checker.
Checking and
That's why they're so attractive.
dynamic testing is the issue. Okay.
Yeah, testing becomes a lot easier with them.
All right. And on communication, I agree with you. People are visual thinkers as far as communication is concerned, and I recommend looking at a financial commentary guy named Morgan Housel, who has a blog post or essay called "The Best Story Wins." So, thank you.
Thank you.